Good morning, good afternoon, good evening. My name is Sam Fuller. I work for NXP Semiconductors, and I'm delighted to be able to talk to you today as part of the ARM Developer Summit. Topic today is edge processing, and we'll be talking about our devices. We'll be talking about the ARM Cassini effort and the importance of standards in making this effort successful. The agenda of this presentation, we'll talk about the edge, we'll talk about standard software platforms, we'll talk about platform security, virtualization and how it relates to new software models, talk about some of the challenges and opportunities around securely connecting to clouds, and then we'll look at some specific SoC devices and capabilities that they have and how they fit into solutions designed for the edge. So edge computing is a relatively new term. It represents a technology that's, I think, been around a long time, but is morphing. As the cloud develops and the technology around cloud data centers develops, there's a lot of innovation in software and secure access and things like that are happening. And when we talk about the edge, we're really talking about leveraging that software model that's been developed into the cloud and migrating that to what has traditionally been embedded computing applications. And when you do this, you have an opportunity to create some new value propositions. In particular, one of the things you can do is, because you're moving stuff out of a cloud, and in cloud data centers, you're essentially charged for the cycles that you use or the data that you store there, you're able to reduce cost for a given workload. You also can increase privacy because you can transmit semantic data. For example, you can kind of reduce the data and maybe anonymize data that gets sent to the cloud, and that increases privacy. You also may be able to do processing locally without having to cross international borders that might have different requirements on data and data storage. By processing locally, you can reduce the amount of data transferred. This would reduce the network costs. So there's computational cost and network costs. So you can reduce network costs by doing that. You also, because you're avoiding these round trips to the cloud for computing, you're able to reduce latency, and that's important in time-sensitive applications. So there are a lot of reasons why it makes sense to do edge computing, and at NXP Semiconductors, we've got a whole business line really focused on the opportunities at the edge. So, you know, we talked about a cloud. I think most people have a concept of what clouds are, and they've been a very high growth industry, a lot of value in moving standard computational workloads to very efficient, very highly scaled data centers. But those data centers in an IoT world need to connect to devices. And there are endpoint devices. So in our homes, we'll have things like thermostats, doorbells, even our mobile phones. There are devices that interact with the cloud. They will interact through gateways because it's the network. There's a hierarchy of devices in the network, and a gateway is simply a device that bridges networks. You have a network in your home, and that network connects through a gateway to a service provider network, which then connects to the cloud. And you might have 20 different machines that you go through in between your device in your home and that cloud, and that all happens pretty quickly. But each of those gateway devices, and especially the gateways in the home, represent opportunities to serve as a platform for edge computing or edge processing. As an example, we can think about using this home example some more. We can talk about opportunities to leverage your home gateway to host workloads in support of maybe your thermostat, maybe your video processing, maybe a health monitoring system. And rather than taking all of the data associated with these applications and moving it to the cloud to be processed, they can be processed locally, and only data that passes a certain threshold or criteria would then be sent to the cloud for action and opportunity. So in order to do that, you can leverage this gateway application to do that processing, and that will result in both lower cloud computing cost, but it also allows your endpoint devices to be reduced in scale and scope. So if I can offload heavier processing tasks to the gateway, then I can make a lighter weight, lower cost endpoint device, my doorbell, my thermostat, or things like that. So there's a lot of opportunity to move workloads and find the optimal way to solve a problem such that we have the most performance system, but also a system that's cost effective, not just for the cost of the equipment, but the actual operating, running of a device. So as we do this, it's important to have a standard software platform. This software is it's really what runs the world now. There's so much software being developed, and one of the most important attributes of software is that there's that it can count on a certain set of services that are available to it. And as over time, software has become, the operating systems, the firmware become very standardized in terms of what they offer. And this slide kind of represents what has been a traditional embedded processing platform. You'd have a multi-core ARM device, you'd have some boot firmware like U-boot or UEFI, then you'd have an operating system. And the operating system would be a standard set of facilities and features that the application environment could depend on. The application would run on top of that. And that's served the embedded world for a long time. One of the problems with this model, though, is that it's pretty shrink-wrap fit. You don't get to, in generally these systems, you develop software on this model, you develop for a piece of target hardware, you co-design those things, you make it work, and once it works, you really can't change it. There are a lot of good reasons why you don't want to change it after that. But as the industry advances, there's a lot of push towards evolving the platform in a couple of ways. So one way, if we look at the top of this diagram, is to add virtual machines. Sometimes we'll have a different form of virtual machine called a container, but the concept is that you're writing software that targets a standard image of whether it's a machine or whether it's a container which essentially standardizes on a kind of an operating system set of services. But by taking advantage of the standardization of that, I can write a piece of software that's more contained, that's less dependent on any hardware attributes running below it, and that I can replicate for scale, and I can also move easily to different platforms and run that software. So that's one attribute of abstraction that's happens, the virtual machine and the platforms associated with that. In the networking world, I spend a lot of time in the networking world. This is also used where we're moving kind of network packet processing workloads that might have been done in the kernel or special hardware. Now we want to do those in a virtual machine or user space. These concepts are often called network function virtualization, or kind of a universal CPE is another acronym referring to building a box it's a pretty generic platform, but depending on the software that I load, I can have it be a firewall, I can be a router, I can have different applications that load and run into that. So there's this evolution of the user space processing and the virtualization environment. Then there's the operating system. Those have evolved, but have essentially serve the same role. The firmware itself is evolved, but essentially serves the same role. But within the firmware, there's this introduction of concepts of secure boot, over-the-air updates that support the whole platform software stack, and trusted execution environments that allow for a set of firmware or software services to run on the platform that are isolated from the traditional operating system and applications. And that isolation provides a mechanism for higher levels of security. And within the next generation platform, there's also a reliance on a root of trust that's a set of hardware that becomes more standardized. The implementations vary a bit, but the set of services are standardized, and then there's a system interface that that the software can depend on to access those hardware services. So once you get all of that in place, then you have the opportunity to support a very robust and broad software ecosystem, much of which is open source, not all of it, but it makes for a very rich environment to develop applications of significant complexity, but because of the standardization of the platform, we're able to support that in a very straightforward manner. And that's I think the importance of standardizing on the ARM architecture and these technologies like Cassini and Parsec and the SystemReady standards, because you can create something that software can depend on, a set of promises that software can depend on and support. So I'd like to spend a few minutes talking about that root of trust and that security. And there's been an evolution over time in terms of what we mean by that. At the very simplest level, there's kind of this trust arc or trust zone capability to create an execution mode within the processor that's separated from and secured from the operating system or any application programs. So the operating system application programs can't spy on, can't understand the code that's operated in that secure execution environment, and can't have access to the memory associated with that. So that's the first level. But without an additional kind of hardware root of trust, some mechanisms to really extract the cryptographic processing, secure boot processing, the key storage, those things, you really can't achieve the level of security that is expected in our modern world. And so you start moving into this need for a baseline platform root of trust. We call it trust architecture within NXP. I think ARM talks about trust islands within their architectures, but the concept is that it's a separate execution environment within an SoC that's responsible for secure execution of code. So if I moved one slide more, we'll see a diagram that shows the kind of what the pieces that need to be in place to support this kind of level 2 of hardening. If you look at this diagram, the left side of the diagram, you talk about the application and OS space. That's where most software lives. It's this rich software environment, and that includes the operating system and the applications. And then there's this trust zone environment, which you could call a trusted execution environment. And that's a separate set of software that runs in its own kind of domain and partition. In that software, you can have applets or kind of trustlets running there for providing certain services like key encryption, data encryption, things like that, where you're taking advantage of hardware. You're not doing it in the rich environment. So you're saying, I have secrets that I don't want anybody to see. I'm going to execute those things in this separate environment. The secure boot facilities, SMMU, those are all kind of are configured and leveraged in this trusted environment. And then there are blocks of hardware within that the trusted environment can leverage. Those include security engines. We call it a SEC engine that would execute a security algorithm like an IPsec or AES algorithm, and it might leverage keys that are only available in this trusted environment to do those operations. So you'd have master keys, you have key encryption keys, those kinds of facilities here. And then you might have secure storage on the device and potentially encrypted storage off the device. But this level of hardening, this is really emerging as a really important requirement. The platform security architecture of ARM defines the features and capabilities required for these various levels. And this is an example of a level 2 requirement in the platform security architecture. Okay, so I'm going to take a little one slide detour now, and I want to just briefly touch on the topic of virtualization. Oh, whoop, we're not at virtualization yet. We're at software. So let me do this, and then we'll jump to the virtualization piece. So so we talked about the need to have these different kind of hardware-based security, and one of the reasons for that is that there are identities within an edge device. There are applications, and the applications may have some access mechanisms and some identity. They're talking to the cloud. Cloud wants to know who they are, and we want to be able to support mechanisms where the identity of a device can't be cloned, can't be corrupted, can't be leveraged in some way by malware. So you have applications, you have the operating system or the firmware itself, you have the system, and maybe even kind of the board or platform. And each of those could have its own kind of unique identity. And generally, when we think about these things, we think about it communicating across the network, the internet. And while we can encrypt that communication, we want to make sure that within the platform itself that the identities are securely held, so that if a piece of malware or some malicious software got onto the platform, that it would not be able to gain access to the identities that are stored on the device. And so as we talked about, that's that hardware root of trust, which is within the hardware of the SoC itself. And then there's a standard API that's provided by Parsec for accessing not necessarily the identities themselves, those can remain hidden, but the interaction with those things. So the standard API methods for these things to be secured is provided by Parsec, and it allows us to kind of differentiate the implementations of this hardware security while having a standard software interface for software. All right. So let me jump to virtualization. I don't want to spend a lot of time on this as we're, but it is important that we recognize. So one thing is virtualization is old technology. It's almost 50 years old. And actually it's more than 50 years old, but it was used in the mainframe world, create these kind of virtual machines that was reused or rediscovered in modern server technology based on not mainframes, but essentially PC servers scaled up, so that there's the virtualization technology that gets used there. And now that virtualization is making its way to the edge and smaller devices. And it's really about the software reuse and the ability to kind of manage the complexity of software with virtualization, be able to reuse it and leverage it in that way. And that's why it's just a powerful abstraction that has a role in the edge. So I've got my edge platform, I've got my virtual machines, I've got my standard software stack and platform, and now I need to go talk to a cloud and connect. Well, in order to do that, I need an identity, and there are credentials, essentially, I don't want to have a system where I'm using a user ID and password to log in, because maybe it's a doorbell. Doorbell, there's no way to enter in your user ID and password on a doorbell. That has to be kind of pre-provisioned. And so for these IoT devices, you need to be able to inject the cryptographic keys and identities in those at manufacture. And then when it's deployed, they need to be able to be correctly linked up to the cloud services they're dealing with. There's a binding that takes place there. But over time, they need to be updated. They need to be able to be revoked or removed from the device. So there's a whole challenge in terms of managing this stuff. Within NXP, we've actually offering a service now to help facilitate this. And the way this works is there is a secure element, which is kind of a security coprocessor. It's a very small, low-cost device that can be pre-provisioned with credentials for whatever service it needs to be provisioned for. And that gets injected or designed into, is a better term, whatever device is needed. And that provides the mechanisms. It does the cryptography for, encrypting. It secures the keys, and it provides that technology that's needed to securely connect to these clouds, support the update of keys and connectivity, offer a zero-touch solution, and a very flexible solution for managing the connectivity of IoT devices to cloud services. Okay, so now I'd like to spend a little bit of time, kind of the remaining time, talking about the systems that make up, that could support the edge. And so to start with that, the first thing to do is to look at, what do these SoCs look like? We've talked about SoCs, and a lot of people are familiar with the kinds of devices that go on our phones and other things. But I'd like to introduce you to something that's that we've developed, called the Layerscape LS2160A. This is a relatively high performance device, but it's designed for use at the edge. It's not designed to use in a data center. It's not a server chip. It's designed at a much lower power dissipation, and it's designed to support kind of these gateway type applications with local processing. It is compliant to the ARM SystemReady SR specifications. It has up to 16 A72 cores, 2 high-performance DDR4 memory controllers. It integrates 6 PCI Express ports. It'll also support SATA. It also can support up to 100 gig Ethernet. And it has various offloads for security and compression. As I mentioned before, it includes that root of trust, kind of trust zone, secure capabilities in it as well. And it can support these virtualized workloads that are being asked to be run on the edge. So whether you're looking for a relatively small system that might have kind of 4, 8 cores, or something as large as this LX2 2160 device, there's a set of kind of price points and performance points to meet the requirements of the workload that you need to run. We also, as part of the ARM Developer Summit, just announced a smaller package version of this, and this is, we call it the LX2 Lite, or the LX2162, and it's a quarter the size, so it's a much smaller package. It does reduce the number of memory controllers to a single memory controller, and reduces the SerDes lanes from 24 to 12. But for a number of these applications, small form factor, kind of ITX form factor boxes, this represents a tremendous amount of processing performance, 64-bit ARM V8 processing performance in a very small, very low power package for use in edge-based processing. So with these kind of products, then you get to the ability to build a low-cost ARM PC with compatibility with ARM SystemReady. So this becomes much more of a PC-like platform. Over the years up until now, most of the use of ARM in edge-type applications are very fit-for-purpose applications. This device has a single function, leverages a traditional software environment, but it's a it's monolithic, or it only does one thing. What we're talking about here is a platform, much more PC-like platform, that runs a standard operating system like Ubuntu or SUSE or CentOS or Red Hat, or associated with this, VMware, ESXi can all run on this platform. And so because of that, and because of this new application programming model and this security inherently built into this, these represent a perfect platform for use in industrial PC, enterprise router, central office type applications, and SD-WAN aggregation applications. So we see the evolution and the introduction of true white box systems to supporting the ARM architecture in edge applications. And I've got a couple to look at right now. First is the NXCOM NSA 6310. This is powered by the LX2160. They've got it available in 8, 12, and 16 core variants. Supports up to 64 gig of memory. It has PCI expandability, so you can put a GPU in it, you can put an FPGA in it. It already has integrated network I/O, in this case up to multi ports for gigabit, 10 gig, and 25 gig. It's designed in a high reliability box. It has dual boot capabilities and redundant power supplies. BMC is built into the device as well. The NXCOM ships this with the NXP LSDK solution, which is Ubuntu based, it essentially leverages an Ubuntu userland. But because it is server ready, it could run any of the OSs that have been developed to run on SystemReady SR with SystemReady SR compiled for the ARM architecture. So wonderful platform there, very high performance and capable. Another one that I wanted to point out is the Solid Run Honeycomb board. So this is designed on a mini ITX platform. So what they did was they actually designed the LX2160 onto a COM Express Type 7 board. So they have that available. And if you have applications where you're using COM Express Type 7, this is a very powerful solution in that form factor. And then that plugs onto an mini ITX platform with a rich set of I/O to create a very nice little embedded development system that can leverage standard M2 PCI peripherals, standard power supplies, standard enclosures around the mini ITX standard. So these do represent great offerings and solutions that are available that can help you move quickly to develop very powerful edge processing systems based on the ARM architecture. So I'd like to take a minute to summarize edge processing, edge computing. I use those terms pretty interchangeably. It offers great benefits to the industry and to the continued development of the IoT. You need standardized platforms like the ARM SystemReady to provide that common software target for software developers. Virtualization is going to be a key technology to be successful, and we're all behind that. Security is also a really key characteristic, and it's not just encryption security. It also includes that trust, that root of trust that has to be built into the silicon from the start. And you need the mechanisms to support that connectivity to the cloud, and there are services around that I think the industry needs to leverage. And within the NXP product portfolio, we have these Layerscape devices and these IDMX devices, all based on the V8 architecture, a very broad, scalable portfolio of solutions for edge processing. And in combination with our microcontroller solutions, we really have, I think, the broadest offering of ARM devices in the industry today. Thank you very much for your time.